Hey everyone, I'm back again with another lecture on chapter 11. This is going to be on water resources. And again, like a couple of chapters ago, we're going to go over some of the same type of material here with regards to the water cycle. So since we've been over it once, I'm going to talk about it again just because it's so important and it's so central to so much stuff that we experience and do and need here on this planet. So I might not cover some of the things in as much detail. I am going to talk about karst a little more in this lesson. So there will be some material that's not covered in the textbook. So hopefully you will watch this because I am going to ask some questions on the quizzes and tests over this material. So getting back to the hydrologic cycle, again, we've already seen this schematic, so you already have an idea about what it is. And basically, it's just how the water cycles through the Earth's environment. That's basically it. The thing is it's a lot more complicated than most people see on a daily basis. We see water coming out of our taps at home when we take a bath or shower. We see water in rivers and lakes. We see water in the ocean. So we're already kind of familiar with parts of this cycle, but it's a lot more detailed and a lot more important than most people realize. There's a whole lot of water under our feet, under the ground. We call groundwater, and that's heavily involved with the karst that I'm going to talk about. So this is a simple water cycle, hydrologic cycle. They're hydrologic and water cycle. It's the same thing. It's just a simpler term. Waters. Everybody knows what water is. So this is a simplified water cycle. You know, it's showing your ice in the mountains, you're showing your snow or rainfall, precipitation, going under the ground, running over land into lakes and streams, into the groundwater. Um, this one, I link this in your lesson, and I highly recommend you all take a look at this. This is USGS, just came out with this a few months ago. This is a much more detailed hydrologic or water cycle, and I put a smaller file on here so I can't zoom in on this slide on this video, but on the website there's a zoomable one so you can zoom in and look at different things. Some of the things that we're going to talk about in this lesson today is we're going to talk about, in chapter 8 we talked about streams and flooding pretty exclusively, and then we talked a little bit about karst. So in this lesson we're going to talk about more about water itself. What are our water resources? Of course, you have the oceans out here. You've got your streams and rivers. We've already talked about those in detail. You've got your ice sheets and ice packs up on the mountains and toward the poles on the Earth's surface. And then you've got a lot of water that we call groundwater down here underneath the surface of the Earth. And that is pretty significant in what we're going to talk about in this lesson because we use a lot of this groundwater. You don't see it necessarily, but it's there. Again, in this area, we talk about it a little bit more because we have the caves and the karst terrain. So it's really intertwined with what our identity is here in South Central Kentucky. But in other places that don't have that kind of unique resource, they don't think about groundwater very much. They don't think about what percentage of their water that they use every day comes from below the ground. Now here, depending on where you grew up, it's much more common now that everybody's on a municipal water supply. That means the water in your homes, it comes from like a county or a city water supply, and that typically is from a lake or a river in this area. However, back in the old days, or if you grew up way out in the country sometimes, that they might not be on that county supply, a lot of people, and almost everyone back prior to 50 years ago, if they lived in the country, they got their water from a well that they dug on their property. So they got it straight out of the ground. And you can see here there's different types of groundwater, different types of aquifers down here. So the water under the ground, the body that it's in is called an aquifer. And you can see here there's actually 3 different aquifers in this one point on the top of the ground because they can be separated by different layers of either rock or some type of material that confines them and keeps them separate from each other. And you can see the cross section here. there are wells drilled down. Some of these wells just go down in this top one, the groundwater. That's what we call the groundwater. But some of them go really, really deep, all the way down to this third one down here. Some places they have to do that. Some places it's more prevalent at the top. You don't have to go that deep. But typically speaking, the deeper the well is, of course, I want to say the more pure the water is. And that, what I mean by that is it hasn't been influenced by humanity any the deeper you go. However, it's not always clean as far as us being able to consume it, because there might be certain minerals in those rock layers that could contaminate it for our use. So it's a fine line between saying something is pure with regards to lack of human intervention versus is it drinkable, or what we call potable. So on the planet, Earth's total water, the vast majority of it is salt water in the oceans. As you look at the globe or any map, you see how immense the oceans are. So 97.2% of the water on the Earth is salt water in the oceans. Only 2.8% is fresh water. So that means for all the people, our whole population on the Earth, all the water that's available, only 2.8% of that, just under 3%, is fresh water that we could use or consume. Of that, almost 77.5% is an ice. So at the poles and in the glaciers in mountainous areas, that is pretty much unusable as well, because we can't access it that well, we can't get to it, we can't transport it. So there's even more that we can't use. And then you have your surface water. Surface fresh water is only 0.5%. So all the water that we have on the surface of this planet, only 0.5% of that actually flows in rivers or is in lakes. So that's tiny. Groundwater is up to 22%. Remember, we're talking about of this 2.8%. That's still a very small amount of the total water on this planet. Some groundwater we can get to very easily, some we can't, and we're going to talk about that more in detail. So when water is in the atmosphere, it falls as precipitation, as we know. Rain or snow, whatever type of precipitation we're talking about. And if you look at this map, this is showing the different colors represent different rates of precipitation. So you can see across the western U.S., it's pretty dry out there. You can see the orange and yellows are drier, less rainfall. But you see up here in the coast, the northwest and northern California coast, huge amounts of rainfall. These are temperate rainforests. To be a rainforest, you have to receive over 100 inches of rainfall per year. So these are what are called temperate, or not tropical. Tropical, they don't have a tropical warm climate. They have more of a moderate climate, so they're temperate rainforests. You see here in Kentucky, if you look at us, we actually get quite a bit of rainfall every year, especially in south central Kentucky. Bowling Green would be about here where my mouse is. We get around 50 to 60 inches of rain per year, which is one of the higher categories in the continental U.S. The only places that get a lot more than that are the higher elevations in the Appalachian Mountains here, and then down on the Gulf Coast some. So we're in a pretty good situation here, and as we've seen the climate change over the last few decades, we're actually receiving more rainfall than in the past. It's actually increasing. Although we're in a drought right now, we haven't gotten much rain in the last couple of months. Overall, we're receiving more rainfall. The biggest change in that is, and I mentioned this in our streams and flooding chapter, is that it's actually changed how it arrives to us, its intensity. Back when I was younger, again, I mentioned this before, I remember we would have rainfalls, but they were just moderate rainfalls, and they might last for a couple of days. Now we get 3 inches of rain from one thunderstorm sometimes. We get these immense amounts of rain very quickly, and that really affects how that, not only flooding and how that water runs off, but it also affects the amount of water in the groundwater, because flooding events actually do not help groundwater as much as a slow, steady type precipitation event does. Because more of the water, the ground can only take up so much water at a time. Once it reaches that capacity, it flows over land into rivers and streams, and that flows on downriver. So if you get a lot at one time, as much water is not able to soak into the earth as it would in a more gradual precipitation event. Here's a chart how we use fresh water. Um, this is in the textbook. We I'll let you kind of look at these things and kind of read about this in the book itself. There's a lot of different ways we use water. Of course, we use it personally to drink. We use it to bathe in. We use it in our toilets. Then you have your industrial use, whatever industry uses. We have our agricultural uses, which is pretty much our largest use of water is our agriculture, growing crops and livestock. Livestock, most people don't think about livestock, but that uses a tremendous amount of water resources. And again, here is another chart showing how we personally use it within our homes. You can see the different categories at the bottom. Our toilets use more water than anything else in the house, and you can go down the list here and see how we use the water. One thing I will point out, you can see showers versus baths. Not many people take baths anymore. Most people take showers, but if you think about it, you're in a shower for maybe, 5 to 10 minutes, depending on how somebody showers. Some people stay in there for 30 minutes, I guess. That water's running constantly all the time. Whereas in a bath, you fill it up, and it looks like a lot, but you're not constantly filling it up. You fill it up once, and then you use it, and it goes away. So luckily in Kentucky, I just showed you, we get precipitation, so we don't really have a water shortage problem here, but out west they do. And that could change drastically, though. With climate change, we don't know how it's going to change. We could start drying up next week and be dry for a long time. We just don't know because we can't really predict those things, how the climate is going to change our precipitation patterns. Now, again, we have surface water, we have groundwater. I'm going to talk about this more as we go. So, groundwater. So, a lot of people kind of don't understand how groundwater works. So, groundwater means that there is water under the ground. And think of it as, let's look at sand, for instance. So, this is kind of a sand, gravelly type dirt or media in the ground. So if you think about gravel, you think about pieces of rock, but in between those pieces of rock, there's tiny spaces where they don't quite fit together just right. So in an aquifer, those tiny spaces are filled with water, so it's saturated. If you think about digging a hole in your yard, and you'll dig down through the dirt, and eventually, if you get deep enough, that hole's going to start filling with water. That's because those little tiny spaces between the particles of dirt are saturated with water. You've reached a water table when that happens. So from there down, all the dirt's going to be saturated with water. That's called the water table, where that starts happening. And you can see here, you've got pieces of clay, and that water, the water molecules get in between those pieces of clay, and this is saturated again. So on the top of the ground, it's still a solid surface and it's solid dirt underneath the ground. It's just when you get to a certain depth, you get to this level and all the pore spaces are saturated with water. Same with gravel and dirt, and the same with rock. Even though rock is solid, like a sandstone, there are still microscopic spaces between the sand grains within sandstone. And water infiltrates that, and it's saturated. So that's where you have these deep aquifers. Sometimes they're inside rock. It's not just unconsolidated material. You can see here if there's cracks and fissures, they'll be filled with rocks. And on the far right, here's where we get our karst, our sinkholes, our caves, and that's what we have here. This is a very different type of aquifer than you're going to see over here. Very different in the way it acts, the way it moves. And this is a good example of this. So I'm going to go back to this. So you can see here that this water is in these tiny little spaces, or even in this rock. So all water is moving. Remember that equilibrium that's been a constant in our lectures. All water is moving toward the lowest base point, which is ultimately the ocean. But it's going to follow the land contours here and the geologic contours of bedrock here. So all water is migrating over time. So when you have a consolidated aquifer like in this clay, or even in something like sandstone, that water is going to move very, very slowly. However, when you have open holes and caves in rock, you basically have a stream flowing underground. So that's going to move more like a surface stream. And that's what this chart is showing right here. So if you have aquifers that is inside rock, the left is the media. The media means what it's in. It's in sediment like dirt, or if it's in rock. That's what the media is. So if you have an aquifer inside a rock, you can see how it might move. Unfractured means no cracks or anything. Down here is how many feet per day this moves. So this is 1 foot right here. So we all know what a foot is. I wish they'd have drawn a line up from this one so we had a point of reference. So this is 1 foot, and every tick mark back is a multiple of 10. So if you go right on this from 1 foot, you go 1 foot to 10 feet, to 100 feet, to 1,000 feet. And if you look up 1,000 feet, where's that water moving that fast? Not much. Most of it is all below 1. It's down here in the microscopic movement level, especially in these bedrocks. Now in the limestone, this is if it's fractured here, that means it's just small cracks. It can be, right here would be about 1 foot a day. But if you have caves, you see where this is going up, 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 and it's actually showing it cuts off at 10,000. It can actually go more than 10,000 feet in a day. Because you think about it, 10,000 feet is what, about 3 miles? And in an open stream that's moving really fast, in Kentucky, we can move water much further than that in some of our larger cave streams. So that means if that water is underground and it comes a big rain and the water is really moving through these cave passageways, it can move very quickly. So what happens to that if we have some kind of an accident and chemical spill into that water? Well, we don't know where it's going, generally speaking. Now, in this area, we study it a lot, so we have an idea. But that pollution could get in there and it can go very quickly, and it can pollute a lot of water in a very short amount of time. That's why, despite what people say, if you have a spring that's popping out of the ground in a karst area, a lot of people say that spring water is the cleanest water and you can drink it. Not in a karst area. I would never trust a spring in a karst area because you don't know what's just up the hill from that spring. If there's a pasture, if there's a cattle lot, you might be getting a lot of pollution into that water, and it might be traveling very quickly to come out in that spring. Also, what you have is when it's going through the pores in the rocks, it's getting filtered a little bit. It's naturally filtered, and that cleans it up. In limestone caves, that's not the case. There is no filtration. That water is just running through a hole in the ground, down to the cave, and flowing out a spring. There's zero filtration in that. So that's something to keep in mind when we talk about karst. In sediment, you see clay is much slower movement. Sand, it speeds up a little bit, and gravel is the least dense, more pore spaces, more openings, so it can move through a gravel medium much, much faster than it can, say, a clay. On top of that, clay particles are expansive, which means when they get wet, they actually expand. So they work to kind of cut themselves off, and they take up pore space in between their individual components because they do expand a little bit. So here's kind of a side view of that. Now, this is not karst. This is our what we call typical aquifers in some kind of media. We have the soil, the media here, which could be gravel, could be sandy, could be loam, could be silt, whatever the case. And that water, we see the brown at the top, that's not saturated. That means that's basically dirt. But if you dug a hole right here, once you got to here, that hole would still be dirt, but it's going to start filling in with water once you get that blue line. And everything under that's going to be underwater. All those pore spaces are going to be saturated. Now, typically, again, this water moves, even underground. It moves down gravity toward the equilibrium. In this case, there's a stream here. So you would have, this would be called a gaining stream because there's going to be springs running into this this stream, and that water from the water tables going into here. So that's a gaining stream. We saw that in chapter 8. Once you go deeper, you see that there are other aquifers under here, but they might be cut off from something. It's called an aquitard, which means it won't let water through it very easily. That might be a layer of rock. It might be some type of sediment like I just mentioned. There are some clays that they expand so much they actually cut themselves off. Water can't go through them. It could be something like that. But you might have different levels of aquifers under any given area. And again, this is showing similar things. It's just showing the water table does drop as it goes down gravity. So under the ground, where a water table might be 10 feet under the surface at one point, it might be a little more than that at another point if it's down slope. And that groundwater is slowly flowing past that. You see here how they drill 2 wells, and the surface of the well is a little bit higher here than the surface of the water in the well, than it is over here. And again, just another example of how groundwater would move. If you have one cut off, like I mentioned before, it's called a confined aquifer. It's unconfined. The unconfined aquifer is the one closest to the surface, where you could dig down to get to the surface of it. That's called an unconfined aquifer. And here is my diagram that you've seen 2 or 3 times now. This is a karst diagram, and this is how our aquifer works. Now, one thing to keep in mind here too. So this is limestone. Limestone's a denser rock than, say, sandstone. But limestone also will be saturated once you get below this water table. So you have the free-flowing water in the passageways here that come out as springs, and it's making its way down through these passageways, gets down to the water table, and flows in these streams, comes out as a spring over here. But the rock itself under this is also saturated. So if you're drilling a well in this area, and this is something that's very important, if you're drilling a water well, and here's a couple of water wells over here that they've kind of stuck in here. So if you drilled a well here, you're probably going to have a dry well. You might intersect a cave passageway here that has a small, tiny little flow in it, but that probably wouldn't be enough to supply water to very much. So you're going to have a dry well because you didn't go deep enough. This well, if you drill down, this well has crossed over where the water table is. So even though it's in solid rock and not hitting a cave, it's still going to have water in the bottom of it. Now here's the difference though in these two. There's a couple of differences actually. The water inside the limestone, the pores in the limestone, is going to be filtered because it's not in a cave, it's not in an open cavity, it's going to be filtered to the grains. But it's going to move so slowly that you're going to pull water out of that hole probably faster than it can recharge flowing through that rock. So it's not going to be probably a very productive well. On the other hand, if you drill down and say this was over here and it tapped into this water here, the open water in the cave, now then you're probably going to have water all the time. It's going to be more reliable. But something else you're going to see is you're going to see when it rains a few hours later, you're going to see your water turn muddy. You might have more pollution in here because, again, this water is getting into these sinkholes and flowing straight down here basically without filtration. So if you dig a well in a karst area and you hit the water inside of a cave, I would absolutely not drink that water. Now, if you're going to use it for watering your lawn or something like that, that would be fine. But I absolutely wouldn't drink water from a well if it's in a karst area that you think might have hit a cave. And we actually go out and look at these things. A few years ago, we had an Amish family that told us, hey, our water, well, the water gets muddy after it rains. Well, you probably shouldn't be drinking that water. They also had a lot of livestock within several sinkholes out there. So I want to show everybody this slide. This is a very interesting slide. We're talking about karst again. You see there's a very lack of surface water here. You might have a stream that flows a short distance, but it disappears. Mostly you have water just funneling down through the sinkholes, right? So this is a map of our local area around Bowling Green. This would be Bowling Green right here. Over here would be Glasgow. This is Edmonson County, Hart County, Simpson County, Allen County right here. And you see all these surface streams, but you see this big area through here that has none. That's what we call the sinkhole plain. And what that is that's exposed limestone on the surface. Now, there's plants and grass and trees on it, but there's no rock on top of it like a sandstone layer that protects it. Therefore, this is covered in sinkholes. And I'm going to show you a picture in just a minute that you're going to be able to see the sinkhole plain. But you see there are hardly any surface streams on here. But that's because any rainfall that falls on this falls onto the ground, goes into the sinkhole, and immediately goes underground into caves. And it generally drains from the southeast to the northwest in this direction right here. Mammoth Cave National Park would be right in this area, the corner of Hart, Barron, and then this corner of Edmondson. This is Mammoth Cave National Park. All of this area right here in northern Barron County flows into Mammoth Cave National Park. And this is heavily farmed in this area. So here is that sinkhole plain. This area, this picture was actually taken right in this area right here near Cave City. And this is an aerial view, and you see it, this looks like craters everywhere. And we can see that because the vegetation, it's just grass. It's pasture land, it's not trees. If you looked in here, it looked the same. You just have trees over here. But you can see it just looks like craters. These are sinkholes, and this is where the water goes. It goes straight underground. And remember our lesson before in mass wasting, subsidence with sinkholes. This is a gradual subsidence. The ground is actually sinking down very slowly into these sinkholes. Now, most of these have stabilized. There's not a lot of activity going on under these right now. And the openings in these sinkholes are small enough that the dirt can be supported so they don't completely cave in, like the picture that you see here of the historic entrance to Mammoth Cave, that a spring is flowing in through and promptly disappearing, or the one at the Corvette Museum that I showed you in that last lesson in Chapter 8. That was a major fall in. You don't see a lot of that out here. You see these more gradual sinkholes. This picture is a spring. This water is actually a perched water table. It's in Mammoth Cave National Park. And what I mean by a perched water table is this rock right here is actually sandstone. It's very impervious to water. It keeps water from going through it. And it's on top of a bunch of limestone down here. Remember, this is limestone. But in Mammoth Cave National Park, we have this sandstone. So water gets into these layers between the sandstone. It flows along this. When it gets to an area where the sandstone's broken up, like this is a small drainage on the surface, and that water is actually flowing out from under that sandstone. It's falling down and entering the limestone, which is down below this. What they're doing right here is called a dye trace. This is environmentally friendly. It doesn't hurt anything in the environment. And what they do is they put this dye into these water sources, and it flows underground. And then we put filters out. And we put these filters out in places we think this water may travel. And what we're trying to do is figure out, okay, if we had something going on here, where's this water going and where's it going to come out down on the Green River? And that's how we map these hydrologic flows underground to understand where the water's traveling. And again, this is a recharged diagram. So we're talking about karst here, and of course you can see that recharges almost immediately after a rainfall event because there's no filtration. It just goes. It flows in and starts running just like a surface stream. But in these confined aquifers and the groundwater itself in a non-karst area, it takes this water a while to move through these zones. And you saw how slow it moves through things like clay and things like normal bedrock. It takes a long time. So if we're pulling out a lot of groundwater, it takes that a long time to recharge from precipitation and rain and all that. It's nothing like karst. So you can see here, this is just kind of a chart showing you that. I'm not going to spend a lot of time on that. So other groundwater sources, we've talked about springs. There are different types of springs. It's not just karst. There are springs in other areas as well. When you have the side of a valley, sometimes you have a lot of springs like coming out of the sides where the rock's broken and the water has a place to get out. Cone depression, I think we see that here in just a couple of slides. Again, this is the same photo I just showed. because this is spring, so I went back to the spring. Some springs like this, these are not karst springs. This is where the water table, the top water table is just flowing down gradient, and it hits a valley, and there's an opening, so it can come out the side of that rock and flow down the side of that valley. Here's your karst springs. This one says it's in Georgia. It looks like probably South Georgia, Florida type aquifer down there. Here's your karst diagram. And then there's a different type of spring where the water actually surfaces from below because it's artesian in nature. And you're going to read about that in your textbook. It has to do with pressure in the head of the groundwater recharge area. I'm not going to get into that a lot in this slideshow, but it's in your textbook. Here's the cone of depression. So if you have a water well and you're pulling water, remember that water takes a while to move through this consolidated material. So if you're pulling it out faster than it's recharging, then you're going to draw that water down, and you're going to have a small cone right there around the well. So that's what a cone of depression is. You'll probably see that in one of your questions later. And here's what a modern water well looks like. It's basically they have a big drill bit. It's hollow. They drill down. I don't remember how many inches wide they are. I think they're 8 to 10 inches wide, maybe smaller than that sometimes. And they put a casing down, which basically is just a metal pipe. And then we have to have a pump to actually pump that water back to the surface. So when we take a lot of water out of an aquifer, in this area it's not a big deal because we get enough rain and our aquifers recharge pretty readily. But when you go out west, when you're pulling water out of an aquifer and it's not getting recharged very quickly, then you have some problems associated with that. They call it groundwater mining. That means they're going in deep and getting water out of an aquifer under the ground. If you're near a coast, salinization is a problem because there's also a saltwater aquifer that's associated with the ocean, and they kind of balance out. But if you take too much fresh water out of one, the salt water can intrude on that. You have the land subsidence. Now, we've talked about that with sinkholes, but if you're taking a lot of water out of the bedrock, believe it or not, even though it's water, it does help both soil and rock keep its rigidness and buoyancy. And once that goes, you could have in weak places some subsidence going on. And then you have to dig deeper, of course. Cone of depression is just an area where they've really depleted their aquifer. You see here around Savannah, Georgia, because they're near the ocean, they use well water a lot, and they've just pulled down that aquifer and extends for several miles away from the city. Here's the saltwater intrusion that I just mentioned. If you're near the ocean and you're pumping water out right near the coast, you're going to have that possibility of, I had that backwards, the salt water is actually green in this case. You have that possibility of that salt water getting over into your freshwater stores if you do that. The Ogallala Aquifer is the most well-known and most studied deep aquifer that we have. It's a huge aquifer, but it's diminishing rapidly with regards to the geologic time because you see here where it's located. It's in the Great Plains that has a lot of agriculture, not as much rainfall as they really need at times. So they really pull from this aquifer to irrigate crops and raise livestock. This aquifer is being tremendously degraded by over-withdrawal. And I think we're okay for a few years, but at some point in the future, probably after I'm gone, there's going to be big problems out there because this aquifer is going to get too low and too expensive to withdraw from. Land subsidence, we've already kind of gone through that. I'm not going to go through this in detail, but you can see where you have that kind of cone of depression, you're going to have land that can subside on top of that. Here, going back to the pictures I've already showed you, the land subsidence and karst areas, the sinkholes, you have an acute, really fast one here, and then you have the more gradual ones in these sinkholes out here. Groundwater, okay, this is selecting a water supply source, so everywhere that has people has to have a water source. So they have to determine, okay, what's our best bet on getting water? Of course, if they're out west and there's not much rainfall, they're going to have to go to groundwater. If you're near a big river or you have a reservoir on a river in your area, that might be a good source. If you have a big enough river, that might be a good source. So there's several factors involved, from quantity to quality. Okay, is this river so polluted we can't use the water? Also delivery. What's the most economical delivery? If we have a lake 50 miles away, is that going to be cheaper to use that water and pipe it over here than digging wells here in this local area? Y'all probably see water towers. If you haven't, just start looking around when you drive, and you will. So all of our water is delivered by gravity, and what that means is it costs a lot of money to pump water, and it's very energy intensive. So what we do is we get our water from a local source, and we pump it one time up into water towers. Typically, you're going to see water towers on higher elevation hills in the area, because once we pump it up once, we rely on gravity to take it back out and over to all the homes and businesses in the area. So that's why you see water towers. One, they're really tall, and two is they're usually located on one of the taller elevations in an area to be able to use gravity as much as possible. We're only pumping it up one time instead of pumping up out to every individual house. They're gravity driven. So that's why if you have strong or weak water pressure in your home, it probably has something to do with your proximity and elevation to your nearest water tower. So alternative sources of water, there are other ways we can get water. We can take water from the ocean and desalinize it, take the salt out of it. There's a couple ways to do that. Distillation is basically you heat it up and you collect the water vapor, the salts fall out, you collect that water vapor, condense it back, and you have fresh, clean water. Reverse osmosis, I'm not going to get into details on that, but basically that's filtering the salt out. You have a thin membrane that gets the salt out of it as it passes through that. So those are potential ways to get water in arid areas along an ocean. It's expensive. It takes a lot of energy, but the technology is there. Reclaimed or recycled water. Now, we actually indirectly do this here, because we take water out of a water source. Let's talk about Bowling Green. Their water source is the Barron River. They take it out of the river, they purify it, they clean it. It's pumped to homes, and then after it's in homes, it's used, whether it's in toilets, showers, whatever it's used in, washing machines, and then it goes to a water treatment plant where it's again cleaned, and then it's put back into the river. So we're kind of recycling our water here, even though we wouldn't call this a recycling system, because we're actually taking it from nature and putting it back in nature. A true recycled system, they're talking more like on site. Like you have a factory that takes water, uses it over and over again. They clean it, use it, clean it, use it. But really, the whole scheme of things, we're recycling all of our water. It's just some of it is done better than others. They clean it better. Some states have better regulations on how clean it has to be when it leaves the treatment plants, etc. We have aquifer storage and rain recovery. We can kind of create artificial aquifers sometimes. We could dig tunnels or mines or whatever the case and use stuff like that. Rainwater harvesting is something that we try to educate people on around here. I have a rain barrel at my house. I use it for my gardening kind of stuff, so I just save some money on the water bill, and it's good for the environment. And what that is, a rain barrel is just attached to your gutters, and every time it rains outside, all the water that runs off in your gutters on your house just goes in that barrel. And you have a water supply that you're not pulling from the Barron River, basically. So we have a lot of homeowners that do that. In my programs that I manage for government, we're getting more farmers to do that, because, again, farming takes a lot of water. And their structures, their barns, they can actually buy large tanks, and they can actually get a lot of water just from rainfall. And they can then use that on their crops or on their livestock or whatever. Irrigation systems, I've already kind of mentioned this. This is when we have to irrigate crops. The Ogallala Aquifer that I mentioned just a minute ago, you're going to see that out there. They're taking water from under the ground and they're putting it on their crops. The problem is the rate that we're taking it out is much faster than how fast it can regenerate and renew itself. So that's going to be a problem out there in years to come. If you all have ever flown out to the western United States, you'll notice from the airplane, if you look out the window and look down, once you pass the Mississippi River and it becomes more common the farther west you go, you look down at the farms and you see big circles of green. Just big, huge circles. And you wonder, why are there circles instead of square fields like we have in Kentucky? That's because those are these irrigation systems that we see on the left. That they wheel around in a big circle irrigating their crops. So that's why those crops are planted in circles. Now, if you look on the right side, this is called drip irrigation. So this type of irrigation over here, the big sprayers that you see, are very inefficient. A lot of that water's evaporating into the air. So they're using a lot more water than they need to. The B picture here, that's being applied closer to the ground. That's better. But drip irrigation, like you see here, is the best because it's just trickling down right around the plants or in a line of plants, and it's hitting the dirt. Not a lot evaporates really quickly, and it's getting straight to the plants. It uses a lot less water as well. Xeriscaping, something we don't really worry about around here. Out west, they, instead of having grass and watering their lawns, they just landscape it. That's what xeriscaping is. And that's it for this lesson. So this wasn't quite as long as Chapter 8. It's a little bit longer than average just because this is such an important topic. And again, it's kind of in my wheelhouse. This is what I do for a living. So I want us to be sure that we're up on these items. And we're going to be talking about, when we get to the last module, more environmental type issues and how we can resolve things. So it's going to be important that you understand some of the components that we're going to be talking about at that point. So again, anytime y'all need anything, just let me know and I'll be happy to help out. Thank you.